Jupiter, the solar system's giant protector or greatest threat. Part 1. The largest planet and its gravity power. Jupiter, a colossal entity, reigns as the largest planet in our solar system, dwarfing all other planets combined. Its sheer mass is staggering, more than 300 times that of Earth. This immense gravitational pull is a fundamental force, shaping its environment and influencing countless celestial bodies around it. This powerful gravity is not just an internal characteristic, but extends far beyond its immediate vicinity, playing a crucial role in the dynamics of asteroids, comets, and even the orbits of other planets. Understanding Jupiter's gravitational dominance is key to comprehending its multifaceted role in our cosmic neighborhood. The planet's internal structure is largely composed of hydrogen and helium, remnants from the early solar nebula. Beneath a thick atmosphere, these elements transition into exotic forms under immense pressure. Gaseous hydrogen gives way to liquid metallic hydrogen, a state where hydrogen atoms are stripped of their electrons, forming a conductive fluid. This vast ocean of metallic hydrogen is believed to be the source of Jupiter's powerful magnetic field, a force field that envelops the planet and extends millions of kilometers into space. The planet's rapid rotation further enhances this dynamo effect, creating a dynamic and complex magnetic environment. The concept of gravity power extends beyond simply holding the planet together. Jupiter's gravitational influence is a continuous dance with smaller objects. It tugs at passing comets, alters the trajectories of asteroids, and choreographs the intricate orbits of its numerous moons. This constant interaction highlights Jupiter not as a static giant, but as a dynamic participant in the gravitational ballet of the solar system. Its very presence acts as a significant perturbation on the orbital paths of countless smaller bodies, continually reshaping the cosmic landscape in its vicinity. The strength of Jupiter's gravity is also responsible for its oblate spheroid shape. Because it spins so rapidly, the material around its equator bulges outwards, making the planet slightly flattened at its poles and wider at its middle. This visible distortion is a testament to the immense centrifugal force generated by its swift rotation and the powerful grip of its own gravity. This distinctive shape provides a visual cue to the dynamic forces at play within and around this gas giant. The study of Jupiter's gravity is not merely an academic exercise, it has practical implications for understanding the long-term stability of the solar system. Precise measurements of its gravitational field help scientists refine models of planetary formation and evolution. By studying how Jupiter interacts with other bodies, we gain insights into the chaotic yet ordered motions that govern our cosmic home. The gravitational ballet orchestrated by Jupiter is a continuous performance, revealing the intricate connections between all members of the solar system. This gravitational dominance also impacts the internal pressure and temperature of Jupiter. The sheer weight of its outer layers compresses the core to extraordinary levels, creating conditions unlike anything experienced on Earth. This extreme environment is responsible for the unique phases of matter found within Jupiter, such as the aforementioned liquid metallic hydrogen. The internal heat generated by this compression and other processes drives much of the atmospheric circulation and weather patterns we observe. In essence, Jupiter's gravity is the invisible hand that guides much of the activity in the outer solar system. It is a constant, pervasive force that defines the planet's very nature and its interactions with the cosmos. From the slightest nudge to the dramatic capture of a comet, Jupiter's gravitational power is a testament to its imposing presence and enduring influence. Its silent strength is a continuous sculptor of the orbital dance around it. The incredible power of Jupiter's gravity is a key factor in understanding its protective role. While it can also be seen as a threat, its dominant gravitational pull has often been theorized as a guardian. It can capture or deflect potentially hazardous objects that might otherwise venture into the inner solar system, a function we will explore further. This dual nature of protection and potential threat is a recurring theme when discussing this magnificent planet. Ultimately, Jupiter's gravity is a constant reminder of the fundamental forces that govern the universe. It is a powerful illustration of how mass dictates destiny on a cosmic scale. Every aspect of Jupiter, from its internal composition to its atmospheric phenomena, is intricately linked to the immense gravitational power it wields. It is a planet where gravity is not just a force, but a defining characteristic that shapes its very being and its impact on the solar system. The gravitational interactions are not static. They are constantly evolving over vast timescales. As Jupiter and other planets orbit the Sun, their combined gravitational fields subtly shift, leading to complex resonances and perturbations. These long-term gravitational dynamics can influence the stability of asteroid belts and the long-period comets, illustrating the ever-changing and interconnected nature of our planetary neighborhood. Part 2. Shield or slingshot, asteroid deflection. Jupiter's immense gravitational field plays a crucial and often paradoxical role in the distribution and trajectory of asteroids and comets within our solar system. For decades, scientists have debated whether Jupiter acts primarily as a protective shield, deflecting dangerous objects away from Earth, or as a cosmic slingshot, sometimes flinging them into the inner solar system. The truth likely lies in a complex interplay of both scenarios, dependent on the specific circumstances of each celestial encounter. One prevailing theory suggests Jupiter's gravity acts as a colossal vacuum cleaner, sweeping up or ejecting many smaller bodies that might otherwise pose a threat to Earth. Its massive presence creates gravitational resonances within the asteroid belt, influencing the orbital paths of countless rocky fragments. These resonances can clear out certain orbital zones, creating gaps known as Kirkwood gaps, while also concentrating asteroids in other regions. This sculpting effect helps manage the population of potential impactors. However, the slingshot effect is also undeniable. As comets and asteroids pass close to Jupiter, its powerful gravity can significantly alter their trajectories. Some objects are indeed deflected away from the inner solar system, their paths elongated into distant, safer orbits. Yet others can be accelerated and flung inwards, sometimes even crossing Earth's orbit. This gravitational kick can turn a relatively benign object into a potential hazard, highlighting the dual nature of Jupiter's influence. The comet Shoemaker-Levy 9 in 1994 provided a dramatic illustration of Jupiter's gravitational power. The comet had been captured by Jupiter's gravity and torn into numerous fragments, which then spectacularly impacted the gas giant over several days. This event demonstrated Jupiter's ability to gravitationally seize and ultimately destroy celestial bodies, thus preventing them from potentially threatening other planets like Earth. It was a stark reminder of the forces at play. Numerical simulations and observational data continually refine our understanding of these interactions. Scientists use powerful computers to model the gravitational dance between Jupiter and countless small bodies, tracing their paths over millions of years. These simulations help to quantify the likelihood of objects being deflected, captured, or accelerated towards the inner solar system, providing crucial insights into the long-term stability of planetary orbits. The asteroid belt, located between Mars and Jupiter, is a prime example of Jupiter's pervasive influence. The gas giant's gravity prevents the material in this region from coalescing into a larger planet. Instead, it remains a fragmented collection of rocky debris, constantly perturbed by Jupiter's pull. Without Jupiter, the inner solar system's dynamics could be vastly different, potentially leading to a much more crowded and hazardous environment. Some researchers argue that while Jupiter occasionally deflects objects towards Earth, its overall net effect is protective. The sheer volume of space it patrols and the number of objects it influences suggest that it prevents more impacts than it causes. This perspective views Jupiter as a cosmic goalie, blocking more shots on goal than it inadvertently sets up. It is a complex balance, often tipping in favor of protection. The role of Jupiter as a gravitational shepherd is crucial for the stability of the entire solar system. Its massive presence helps to regulate the flow of smaller bodies, preventing a constant bombardment of the inner planets. While individual events might seem threatening, the long-term averages suggest a more benevolent influence. It is a continuous, dynamic process that shapes our cosmic environment in profound ways. Understanding Jupiter's dual role as both a potential threat and a protector is vital for assessing long-term risks to Earth. Continued monitoring of near-Earth objects and improved computational models help us track these gravitational interactions. By studying Jupiter's complex dance with asteroids and comets, we gain a deeper appreciation for the intricate gravitational ballet that governs our solar system, highlighting its critical importance. In conclusion, Jupiter's influence on asteroids and comets is a multifaceted phenomenon. It acts as both a formidable shield, deflecting and capturing countless objects, and at times, an inadvertent slingshot, altering paths in unpredictable ways. This dynamic interplay underscores the profound gravitational power of the gas giant, and its indispensable, albeit complex, role in shaping the orbital environment of our solar system. Part 3: The Great Red Spot and Megastorms. Jupiter is renowned for its spectacular and often violent atmospheric phenomena, most notably the iconic Great Red Spot. This colossal storm, larger than Earth itself, has been raging for at least 350 years, making it the longest-lived storm in our solar system. It is a swirling vortex of reddish clouds, driven by powerful winds and sustained by the planet's internal heat and rapid rotation. The Great Red Spot is a powerful testament to the turbulent and dynamic nature of Jupiter's atmosphere. The reddish hue of the storm is thought to be caused by complex chemical reactions occurring within its upper atmosphere, involving compounds like phosphorus or sulfur, brought up from below. The exact mechanisms are still under investigation, but it is clear that the intense energy and circulation within the spot create a unique chemical environment. The high-altitude clouds within the storm are also colder than their surroundings, indicative of its immense vertical extent. Beyond the Great Red Spot, Jupiter's atmosphere is a maelstrom of activity. Powerful jet streams, much like Earth's but on a grander scale, encircle the planet. These atmospheric currents create distinct bands of alternating color, from the lighter zones to the darker belts, each representing different atmospheric conditions and wind speeds. The interaction between these zones and belts generates smaller, yet still enormous, storms and eddies that constantly swirl and evolve. While the Great Red Spot is the most famous, Jupiter hosts numerous other cyclonic and anticyclonic storms, some of which are hundreds or even thousands of kilometers across. These storms can merge, dissipate, or even change direction, creating an ever-shifting tapestry of atmospheric chaos. The constant churn and interaction of these weather systems make Jupiter a living laboratory for studying extreme meteorology. The energy driving these megastorms comes from a combination of sources. The planet's rapid rotation creates powerful Coriolis forces, which help organize the atmospheric flow. Additionally, internal heat radiating from Jupiter's core contributes to the convection currents that fuel these storms. This internal heat source, a remnant from the planet's formation, helps maintain the temperature differences necessary for such vigorous atmospheric circulation. Observations from space probes like Juno have provided unprecedented detail into the structure and dynamics of these storms. Juno's microwave radiometer, for example, can peer beneath the visible cloud tops, revealing the three-dimensional structure of atmospheric features and the mechanisms driving the deep circulation. These insights are crucial for understanding how such long-lived and massive storms are sustained. Scientists are particularly interested in understanding why the Great Red Spot has persisted for so long. Theories include its immense size, which allows it to absorb smaller storms, effectively feeding itself, and its position between strong opposing jet streams that act to contain it. The stability of its structure within Jupiter's dynamic atmosphere remains a subject of ongoing research and fascination. The study of Jupiter's storms is not just about understanding another planet. It provides a unique perspective on atmospheric physics. Earth's weather systems are complex, but Jupiter's offer a magnified view of fundamental fluid dynamics under extreme conditions. Insights gained from Jupiter can help us refine our models of atmospheric circulation and storm behavior, potentially even improving our understanding of Earth's climate. The sheer scale and longevity of Jupiter's storms, especially the Great Red Spot, are a powerful reminder of the diverse and extreme environments that exist within our own solar system. They represent a dynamic interplay of physical forces on a grand scale, constantly reshaping the face of this gas giant. The vibrant, chaotic beauty of Jupiter's atmosphere is a captivating spectacle of nature's power. Future missions to Jupiter will undoubtedly continue to unravel the mysteries of its megastorms, providing even more detailed images and data. Each new observation brings us closer to understanding the intricate mechanisms that drive these colossal atmospheric engines, deepening our appreciation for the complex meteorological wonders of the gas giant. Part 4. Moons of Jupiter as Alien Worlds. Jupiter, far from being a solitary wanderer, is accompanied by a vast retinue of moons, currently numbering 95 confirmed satellites. These moons are not mere rocks. They are diverse, captivating worlds, each with its own unique characteristics and geological history. The four largest, known as the Galilean moons Io, Europa, Ganymede, and Callisto, are particularly fascinating, offering a glimpse into planetary processes that differ dramatically from those on Earth. Their individuality makes them compelling subjects for scientific exploration. Io, the innermost of the Galilean moons, is perhaps the most volcanically active body in the entire solar system. Its surface is dotted with hundreds of volcanoes, constantly erupting plumes of sulfur and sulfur dioxide, giving it a vibrant, mottled appearance of yellows, oranges, and reds. This extreme volcanic activity is driven by immense tidal forces exerted by Jupiter and its neighboring moons Europa and Ganymede, which stretch and squeeze Io, generating intense internal heat. Europa, slightly smaller than Earth's moon, is renowned for its smooth, icy crust, crisscrossed by myriad cracks and ridges. Beneath this frozen shell, scientists believe a vast saltwater ocean exists, warmed by tidal heating. This subsurface ocean is considered one of the most promising locations in the solar system for extraterrestrial life, sparking intense interest and fueling future mission proposals aimed at exploring its depths. Its pristine, icy surface hints at a hidden, dynamic world. Ganymede stands out as the largest moon in the solar system, even surpassing the planet Mercury in size. It is unique among moons for possessing its own intrinsic magnetic field, a characteristic typically found only in planets. Its surface is a patchwork of ancient, heavily cratered terrain and younger grooved regions, indicative of past geological activity. This complex surface history suggests a dynamic internal structure and evolution over billions of years. Callisto, the outermost of the Galilean moons, is a heavily cratered, ancient world, showing little evidence of significant geological activity since its formation. Its surface is considered one of the oldest and most heavily pockmarked in the solar system, providing a valuable record of impacts from the early solar system. Unlike its inner siblings, Callisto experiences less intense tidal heating, leading to a more quiescent and unchanging exterior. Beyond the Galilean moons, Jupiter hosts a vast collection of smaller, irregular satellites, many of which are thought to be captured asteroids or comets. These distant moons often have highly eccentric and inclined orbits, further illustrating Jupiter's immense gravitational reach. They represent a diverse population of cosmic wanderers, each with its own story of capture and orbital evolution within Jupiter's immense sphere of influence. The study of Jupiter's moons provides crucial insights into the formation and evolution of planetary systems in general. Their diverse compositions, geological features, and internal structures offer a natural laboratory for understanding how celestial bodies respond to gravitational forces, internal heating, and external bombardment. Each moon is a unique case study in planetary science. Future missions, such as Europa, Clipper, and JUICE, are specifically designed to delve deeper into the mysteries of these Jovian satellites, particularly focusing on their potential for harboring life. These missions aim to characterize their subsurface oceans, investigate their compositions, and search for signs of active geological processes, pushing the boundaries of our understanding of habitability beyond Earth. In essence, Jupiter's moons are far more than just celestial companions. They are distinct alien worlds, each with its own compelling narrative. From the fiery inferno of Io to the potentially life-bearing ocean of Europa, they represent the incredible diversity and wonder of our solar system, challenging our perceptions of what a moon can be and inspiring ongoing exploration. The sheer variety among these moons highlights the profound influence of proximity to the gas giant and the varying degrees of tidal heating they experience. This gradient of gravitational interaction is a key factor in shaping their individual destinies, leading to such dramatically different worlds orbiting a single parent planet. Part 5. Europa, Ganymede, and Habitability. Among Jupiter's captivating retinue of moons, Europa and Ganymede stand out as prime candidates in the search for extraterrestrial life within our solar system. While neither surface appears hospitable in the conventional sense, compelling evidence suggests both moons harbor vast subsurface oceans of liquid water, an essential ingredient for life as we know it. The potential habitability of these icy worlds has ignited immense scientific curiosity and driven ambitious space exploration initiatives. Europa, in particular, has become a focal point for astrobiological research. Its smooth, cracked, icy shell strongly suggests the presence of a global ocean beneath, potentially twice the volume of all of Earth's oceans combined. This ocean is thought to be kept liquid by tidal heating, generated by Jupiter's immense gravitational pull, which flexes and warms the moon's interior. The interaction between rock and water on the seafloor could provide chemical energy sources for life. Evidence for Europa's ocean includes observations of its magnetic field, surface fractures that suggest movement of an underlying liquid, and even possible plumes of water vapor detected erupting from its south pole. These plumes, if confirmed, could offer a direct way to sample the ocean's composition without having to drill through kilometers of ice, revolutionizing the search for biosignatures. The prospect of direct sampling is incredibly exciting. Ganymede, the solar system's largest moon, also harbors a subsurface ocean, though it is believed to be much deeper and sandwiched between layers of ice. Its ocean is thought to be kept liquid by a combination of residual heat from its formation and ongoing tidal heating. The presence of its own magnetic field, unique among moons, suggests a metallic core and a dynamic interior, further supporting the idea of a geologically active world capable of sustaining a long-lived ocean. While Ganymede's ocean is likely less accessible than Europa's, its sheer size and internal dynamics make it another compelling candidate for habitability. The potential for water-rock interactions at the base of its ocean, similar to hydrothermal vents on Earth, raises the possibility of chemical energy pathways for life to emerge and thrive. The vastness of its interior points to immense potential. The concept of habitability extends beyond just the presence of liquid water. Scientists also look for sources of energy, essential chemical elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and suitable environmental conditions, such as temperature and pressure ranges. The tidal heating on Europa and Ganymede provides not only the heat for liquid water, but also potentially the energy gradients that could drive metabolic processes. Future missions, like NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer, JUICE, are designed to investigate these moons in unprecedented detail. Europa Clipper will conduct numerous close flybys of Europa to characterize its ocean, ice shell, and potential plumes. JUICE will perform extensive observations of Ganymede, Europa, and Callisto, focusing on their ocean characteristics and potential for life. The exploration of Europa and Ganymede represents a frontier in astrobiology, pushing the boundaries of where we expect to find life. These icy worlds challenge our Earth-centric view of habitability, suggesting that life could thrive in environments far different from our own, sustained by internal energy rather than direct sunlight. The implications for the prevalence of life in the universe are profound. Even if no active life is found, understanding the geochemical processes at play in these subsurface oceans will provide invaluable insights into the conditions that could lead to the emergence of life. It's a journey not just to find life, but to understand its origins and the vast spectrum of environments where it might exist. The mysteries held within these frozen worlds continue to inspire awe and scientific endeavor. The presence of liquid water under kilometers of ice is a remarkable testament to the diverse ways energy can be generated and sustained in the solar system. These moons remind us that the search for life should extend beyond the habitable zone, embracing all places where the fundamental ingredients for life can converge, regardless of surface conditions. Part 6. Jupiter's Magnetic Field and Radiation Belts. Jupiter boasts the most powerful magnetic field of any planet in our solar system, a colossal force field that profoundly influences its environment and extends millions of kilometers into space. This immense magnetosphere is generated by the rapid rotation of the planet's liquid metallic hydrogen core, a phenomenon known as a planetary dynamo. The strength and sheer scale of Jupiter's magnetic field are unparalleled, creating an extreme and dynamic region around the gas giant. This magnetic field is roughly 20,000 times stronger than Earth's, dominating a vast region of space known as the Jovian magnetosphere, Within this magnetosphere, charged particles from the solar wind and those originating from Jupiter's volcanically active moon Io are trapped and accelerated. These particles form intense radiation belts, similar in concept to Earth's Van Allen belts, but far more powerful and hazardous. The radiation belts around Jupiter are incredibly harsh, posing significant challenges for any spacecraft attempting to study the planet and its inner moons. The high-energy electrons and ions within these belts can damage electronic components and pose a threat to biological systems. Engineers designing missions to Jupiter must incorporate extensive radiation hardening to protect their instruments and ensure mission longevity. Io plays a critical role in feeding Jupiter's radiation belts. Its continuous volcanic eruptions spew vast quantities of sulfur, oxygen, and other gases into space. These particles become ionized by sunlight and then swept up by Jupiter's powerful magnetic field, forming a donut-shaped torus of plasma that orbits the planet. This plasma torus is a significant source of the charged particles that populate the inner magnetosphere. The interaction between Jupiter's magnetic field and its moon Ganymede is particularly interesting. Ganymede is the only moon in the solar system known to have its own intrinsic magnetic field. This smaller magnetosphere is nested within Jupiter's giant one, creating a complex magnetic interaction. Studying this interaction helps scientists understand how planetary magnetic fields are generated and how they interact with their environments. The magnetosphere acts as a shield, deflecting the solar wind and protecting Jupiter's atmosphere from being stripped away. However, it also channels charged particles towards the planet's poles, creating spectacular and powerful aurorae. These Jovian aurorae are far more energetic and extensive than Earth's, visible across a wide range of wavelengths, from ultraviolet to infrared, showcasing the immense power within the magnetosphere. Understanding Jupiter's magnetic field is crucial for unraveling the planet's internal structure and dynamics. Measurements of the magnetic field's strength, orientation, and variability provide clues about the depth and properties of the metallic hydrogen layer where the dynamo operates. It helps scientists paint a more complete picture of what lies beneath Jupiter's turbulent cloud tops. Missions like Juno have been specifically designed to investigate Jupiter's magnetic field with unprecedented precision. Juno's highly elliptical orbit allows it to dip low over the planet's poles, directly sampling the magnetic field and the particles within the radiation belts. The data collected by Juno are revolutionizing our understanding of this extreme magnetic environment and its origins. The study of Jupiter's magnetosphere and radiation belts provides valuable insights into fundamental astrophysical processes. It offers a natural laboratory for understanding how planetary dynamos work, how plasma interacts with magnetic fields, and how radiation environments are formed and sustained in extreme cosmic settings. Jupiter is a magnificent demonstration of electromagnetism on a grand scale. In essence, Jupiter's magnetic field and its associated radiation belts are integral to its identity as a gas giant. They define a vast, energetic region of space that is both a protective barrier and a dangerous environment, continuously sculpted by the planet's internal dynamics and external interactions. Part 7. Juno Mission Discoveries. The Juno mission, launched by NASA in 2011 and arriving at Jupiter in 2016, has revolutionized our understanding of the gas giant, providing unprecedented insights into its origins, atmosphere, interior, and magnetosphere. Designed to peer beneath Jupiter's dense cloud tops, Juno's suite of instruments has unveiled a planet far more complex and dynamic than previously imagined, challenging long-held theories about gas giant formation. Its polar orbit has been instrumental in these discoveries. One of Juno's most significant findings concerns Jupiter's magnetic field. While already known to be powerful, Juno data revealed that the field is even stronger and more irregular than expected, with significant anomalies. It also showed that the magnetic field is generated closer to the surface, within the metallic hydrogen layer, rather than in a deeper, more concentrated core. This challenges models of uniform dynamo generation and indicates a more complex internal structure. Juno also made groundbreaking observations of Jupiter's majestic aurorae. It captured stunning images and data showing how particles from Jupiter's intense radiation belts are funneled along magnetic field lines into the polar regions, creating brilliant displays of light. The mission revealed that Jupiter's aurorae are more powerful and dynamic than previously thought, driven by mechanisms distinct from Earth's. Regarding Jupiter's interior, Juno's gravity science experiments have been particularly revealing. By precisely measuring tiny variations in Jupiter's gravitational field, scientists have deduced that the planet's core is far from a compact, solid ball. Instead, it appears to be a diffuse, fuzzy core, potentially larger and less distinct than predicted, mixing with the overlying metallic hydrogen. This suggests a different formation scenario for gas giants. The mission has provided invaluable data on Jupiter's deep atmosphere. Juno's microwave radiometer, capable of penetrating the thick cloud layers, revealed that the famous colorful bands and zones extend much deeper into the planet than anticipated, far beyond the visible cloud tops. It also detected giant cyclones at Jupiter's poles, arranged in geometric patterns, a phenomenon completely unexpected and unique in the solar system. Juno's observations of atmospheric ammonia have also been surprising. Instead of being uniformly mixed, ammonia is highly concentrated in certain regions, indicating a complex and active atmospheric chemistry that plays a crucial role in cloud formation and dynamics. The ammonia gas is involved in ammonium hydrate cycles, similar to water cycles on Earth, but with different chemicals. The mission's study of Jupiter's storms, including the Great Red Spot, has provided new perspectives. While the Great Red Spot's depth is still being fully understood, Juno data indicates that many powerful storms penetrate far below the visible cloud deck, extending hundreds of kilometers deep. This highlights the immense energy and vertical extent of these atmospheric behemoths. Juno's high-resolution images have also captivated the public, showcasing the stunning beauty and chaotic complexity of Jupiter's cloudscapes, from swirling vortices to intricate patterns of ammonia ice. These visuals are not just aesthetically pleasing, they provide critical context for the scientific data, allowing researchers to correlate atmospheric features with underlying physical processes. In summary, the Juno mission has fundamentally reshaped our understanding of Jupiter, turning many theoretical assumptions into concrete discoveries. It has unveiled a planet that is far more dynamic, complex, and mysterious than previously envisioned, continually inspiring new questions and avenues for future exploration of gas giants. Juno is an ongoing testament to innovative space exploration. The data from Juno continue to be analyzed, promising even more breakthroughs in our understanding of how giant planets form and evolve, not just in our solar system, but also exoplanets around distant stars. Its legacy will undoubtedly influence planetary science for decades to come, providing a rich data set for further research. Part 8. Jupiter's role in forming the solar system. Jupiter's immense mass and powerful gravitational field were not merely passive features. They played a pivotal and dynamic role in shaping the very architecture of our solar system during its tumultuous formation period. Its early presence as a rapidly accreting gas giant profoundly influenced the distribution of matter, the orbits of other planets, and the eventual stability of the entire planetary system. Jupiter truly was a cosmic architect. In the early solar nebula, as dust and gas began to coalesce, Jupiter grew rapidly, quickly becoming the dominant gravitational force after the Sun. Its strong gravity likely carved out a wide gap in the protoplanetary disk, influencing the amount of material available for the formation of other planets. This sweeping action helped define the boundaries and compositions of the inner, rocky planets and the outer icy bodies. One prevailing theory, the Grand Tack hypothesis, suggests that Jupiter did not always reside in its current orbit. Instead, it may have migrated inwards towards the Sun, potentially as far as Mars's current orbit, before reversing course and migrating back outwards to its present position. This gravitational excursion would have had profound consequences, scattering debris, clearing out the inner solar system, and potentially driving the formation of the asteroid belt. This inward and outward migration would have been instrumental in the formation of Mars, explaining its relatively small size compared to Earth and Venus. Jupiter's gravitational perturbations during its inward tack would have disrupted the accumulation of material in the region where Mars was forming, starving it of the necessary building blocks to grow into a larger planet. It effectively stunted Mars's growth. Jupiter's powerful gravity also played a crucial role in preventing the material in the asteroid belt from coalescing into a fifth terrestrial planet. Instead, its gravitational influence continuously stirred and perturbed these rocky fragments, leading to collisions and fragmentation rather than accretion. This explains why the asteroid belt remains a collection of small bodies rather than a coherent planet. The gas giant's influence extended to the outer solar system as well. Jupiter's gravity is thought to have scattered vast quantities of icy planetesimals outwards, contributing to the formation of the Kuiper belt and the more distant Oort cloud. These icy reservoirs are now the source of many comets that occasionally visit the inner solar system, a testament to Jupiter's early, far-reaching impact. Furthermore, Jupiter's mass helped to stabilize the orbits of the other giant planets, Saturn, Uranus, and Neptune, through gravitational resonances. This stability, established early in the solar system's history, was crucial for the long-term evolution of all the planets, including Earth, ensuring relatively predictable and unperturbed orbits for billions of years. It was a crucial balancing act. Without Jupiter, our solar system would likely be a drastically different place. The inner solar system might have been bombarded by far more comets and asteroids, or perhaps formed more planets. The outer solar system would lack its current configuration of icy bodies. Jupiter's presence was a formative event, establishing many of the characteristics we observe today. The study of Jupiter's role in solar system formation is an active area of research, with new models and observational data continuously refining our understanding. By understanding how this colossal planet emerged and evolved, we gain deeper insights into the complex processes that led to the creation of our planetary home and, by extension, other planetary systems throughout the galaxy. In essence, Jupiter was not just a planet that formed, it was a fundamental force that shaped the creation, evolution, and long-term stability of the entire solar system. Its gravitational influence acted as a cosmic sculptor, guiding the building blocks of planets and defining the architecture of our cosmic neighborhood. Part 9. Jupiter in Myths and Ancient Astronomy. Long before telescopes revealed its swirling clouds and numerous moons, Jupiter held a prominent place in the myths, legends, and astronomical observations of ancient civilizations around the world. Its sheer brightness and distinctive slow movement across the night sky made it easily identifiable, leading cultures to imbue it with immense power and significance, often associating it with their chief deities and kings. It was a celestial beacon, inspiring awe and reverence. In Roman mythology, Jupiter was the king of the gods, equivalent to the Greek god Zeus. He was the god of sky and thunder, wielding immense power and authority over both mortals and immortals. This association with the supreme deity reflected the planet's dominance and majesty in the night sky. The very name Jupiter carries this legacy of ultimate power and regal authority, a testament to its imposing presence. The Greeks also revered the planet as Zeus, their most powerful god, associated with justice, order, and the heavens. They observed its stately procession across the constellations, interpreting its movements as divine pronouncements or omens. The grandeur of the planet resonated deeply with the attributes of their ruling deity, solidifying its celestial importance in their worldview. To the Babylonians, who were astute astronomers, Jupiter was associated with their chief god Marduk, the patron deity of Babylon. They meticulously tracked its movements and used these observations for astrological predictions and calendrical purposes. Their sophisticated astronomical tables demonstrate a deep understanding of Jupiter's orbital period, showcasing their advanced scientific capabilities. In ancient Chinese astronomy, Jupiter was known as the wood star and was associated with the element wood in their five-element system. Its orbital period of approximately 12 years roughly corresponded to their zodiacal cycle, leading to its inclusion in their intricate calendrical and astrological systems. Its movements were seen as important indicators of earthly events and prosperity. Hindu astronomy refers to Jupiter as Brihaspati, often depicted as a revered guru or teacher of the gods. Brihaspati is the largest and most auspicious planet in Vedic astrology, symbolizing wisdom, knowledge, and prosperity. Its benevolent influence was sought after and integrated into their astrological interpretations, reflecting the planet's perceived positive impact. The Maya civilization, known for their sophisticated understanding of cycles and time, also observed Jupiter. While their focus was often on Venus, they integrated the movements of other planets, including Jupiter, into their complex calendar systems and astronomical tables. These observations were critical for their intricate ritual practices and understanding of cosmic order. The consistent theme across these diverse cultures is the recognition of Jupiter's prominence and its association with powerful, often benevolent, deities or forces. Its slow, deliberate journey through the stars suggested a steadfast and influential presence, a cosmic ruler overseeing the celestial realm. This pervasive cultural significance highlights humanity's long-standing connection to the cosmos. Even without the aid of modern instruments, ancient astronomers were able to track Jupiter's motion, predict its appearances, and develop remarkably accurate models based on naked-eye observations. This demonstrates an incredible dedication to celestial observation and a profound capacity for abstract thought, laying the groundwork for future scientific inquiry. Thus, Jupiter's legacy extends far beyond its physical attributes. It is deeply embedded in the cultural and intellectual history of humankind. From mythical kings to astronomical benchmarks, Jupiter has consistently inspired awe, informed belief systems, and driven scientific observation for millennia, a truly universal symbol of power and majesty. Part 10. Could Jupiter ever threaten Earth? While Jupiter is often lauded as the great protector of the inner solar system, its immense gravitational power also harbors the potential to pose a threat to Earth, albeit under very specific and highly improbable circumstances. The relationship between the two planets is a complex gravitational dance, usually benevolent but with theoretical scenarios that suggest a darker side to the gas giant's influence. It's a delicate cosmic balance. The primary way Jupiter could threaten Earth involves its ability to gravitationally perturb objects in the asteroid belt or the Kuiper belt. While it mostly shepherds or deflects these bodies, a close gravitational encounter could, in rare instances, slingshot a comet or asteroid onto an Earth-crossing trajectory. Such an event would be highly unpredictable and dependent on precise celestial alignments, making it extremely rare. A more direct, though equally unlikely threat could arise from a radical change in Jupiter's own orbit. If, for some reason, Jupiter's orbit were to become significantly more eccentric, or to cross into the inner solar system, its gravitational influence would wreak havoc. It could destabilize the orbits of all the inner planets, potentially ejecting Earth from the solar system or sending it spiraling into the Sun. However, current models suggest Jupiter's orbit is remarkably stable. Another theoretical scenario involves Jupiter's moons. If a significant celestial event were to destabilize one of Jupiter's larger moons, like Europa or Io, causing it to break apart or be flung out of orbit, the resulting debris field could pose a long-term, though low probability, threat to Earth. This catastrophic event would require an extraordinary external force to occur. The potential for Jupiter to capture a rogue object and then direct it towards Earth is also a theoretical concern. While Jupiter often captures objects into its own orbit, like the comet Shoemaker-Levy 9, a particularly unlucky sequence of gravitational interactions could, in a rare turn, put such a captured object on a collision course with our planet. The universe is full of chaotic possibilities. It is important to emphasize that these threatening scenarios are highly improbable and would unfold over vast cosmic timescales, often millions or billions of years. Our solar system has achieved a high degree of orbital stability over its 4.5 billion-year history, largely due to Jupiter's stabilizing influence, rather than its destabilizing potential. The current configuration is robust. Modern astronomical observations and sophisticated computer simulations continually monitor the orbits of planets and known near-Earth objects. These studies provide reassurance that no immediate or foreseeable threat from Jupiter's gravitational influence is on the horizon. The long-term gravitational ballet of the solar system, while complex, is generally predictable. Ultimately, Jupiter's protective role far outweighs its theoretical threat. By acting as a massive gravitational sink, it has likely cleared out more potentially hazardous objects from the inner solar system than it has ever directed towards us. Its immense mass has been a crucial factor in shielding Earth from a more frequent bombardment over geological time. So, while the colossal gas giant possesses the raw gravitational power to theoretically threaten Earth, the reality is that Jupiter is, and has been, an indispensable guardian of our cosmic neighborhood. Its existence is more a blessing than a curse, ensuring a relatively stable and less hazardous environment for life to flourish on our small blue planet. The scenarios where Jupiter poses a direct threat are mostly confined to theoretical physics and highly improbable long-term gravitational dynamics. For all practical purposes, Jupiter remains our solar system's colossal protector, a silent sentry against a more chaotic cosmic environment.